Hey there, it's Shannon Myers. Welcome to Discrete Probability Density Functions, also known as Discrete Probability Distributions. So, what is a discrete probability density function or distribution? It is a model that gives the probability for each event in the sample space. It is often expressed in the format of a table and/or a probability histogram. For a random variable to be discrete, it must have a finite number of events that can happen in its sample space. The sum of the probabilities corresponding to all of the simple events in the sample space must sum to 1. Very good. Note, in some textbooks or papers, if a probability that is extremely small but not exactly 0, so not impossible but practically impossible, such as like 0.000000321 or something, it's often written as 0 plus so that you can see that it wasn't impossible, but also that it was very, very small. So let's think about 2 examples of discrete random variables. What do you think? We worked with a couple of them. Good. You could flip a coin, right? Maybe, I don't know, 3 times. And you want to, know what your random variable is. So what is your interest? So you want to find maybe the probability of getting a tail. A tail. How about, I don't know, you think of one. Well, I'm making this video in October, so it could be that you have a bag of assorted candies for Halloween and you want to find the probability of reaching in the bag, and selecting I'm going to say Butterfinger because I like Butterfingers. Butterfinger candy. Four times without replacement. So in the first case, what kind of trials would those be? Would they be dependent or independent? Good. They would be independent, right, for the first one, because one flip of the coin does not influence the following flipping of the coin, or the next flip of the coin. If you've got a fair coin, nothing weird. But with reaching into the bag, selecting a candy and not replacing it is definitely dependent. It's going to change the probabilities. So this would be dependent. Okay? Very good. All right. And here we go. 0 has to be less than or equal to each probability of an event in the sample space, which has to be less than or equal to 1. okay, for each value of x. Actually, where x is your random variable, all right, your event of interest, if you will. Okay, so let's take a look at what we have going on, all right? Suppose that we roll 2 fair-sided dice, fair 6-sided dice. Let's check out the situation. Let's make a chart. Okay, so, one way to look at these things is what can you possibly roll? 6 sides. So on the first die, you could roll a 1, a 2, a 3, a 4, a 5, or a 6. And the same with the second one. Each roll of the dice is going to be good, independent, right? So we can use the general multiplication rule without having to worry about subtracting anything out, or not subtracting, but changing out probabilities. And let's see, what we're looking at is, okay, what are the possible sums that we can get in rolling 2 dice? So if you roll a 1 and a 1, what can you get? Good. 2, and you just kind of work your way. A 1 and a 2 would be 3. 1 and 3 would be 4. 1 and 4 would be 5. And then 6, and then 7. Make sense? And then what's going to happen here? Well, we have 3, 4, 5, 6, 7, and 8. And then 4, 5, 6, 7, 8, and 9. 5, 6, 7, 8, 9, and 10. 6, 7, 8, 9, 10, and 11. And then 7, 8, 9, 10, 11, and 12. Okay, so we've modeled every possible situation that can happen with 1 roll of 2 dice. So let's check this out. All right, let's do some of these probabilities. What's the probability of rolling a 4? How many ways could we get a 4 on a single roll of 2 dice? Good. You see right here, these are all the ways you can sum to 4, right? So you could get a 3 and a 1. You could get a 2 and a 2. You could get a 1 and a 3. All right, so that takes care of all possibilities. Well, there's 3 ways that event can take place, the event of rolling a 4. And how many total probabilities are in this space? Beautiful. If you count all the squares, there's 36 simple events that can happen. So this one down here will get 3 out of 36, which of course is 1/12. Cool, cool? All right. What about the probability of rolling doubles? Good. The doubles are all here, aren't they? If you check it out, they're all on that diagonal. So the probability of rolling doubles ends up being what? How many ways? Perfect. 6 out of 36, which reduces to be 1/6. Cool so far? Alrighty. Well, next up, what do we have? We have the probability of rolling a 7. And so if you think about, I don't know if you've ever played craps, right? But if you think about it, let's look at how many ways that we could roll a 7. There's the same number of ways that you could roll a 7 as you can roll doubles. So 7 is going to be the most repeated single number. Make sense? All right, perfect. So let's see what that probability is. It's the same as the probability of rolling doubles. So 6 out of 36, which is 1/6. All right, so what about the complement of that, the probability of not rolling a 7? Well, we've already found the probability of rolling a 7, right? So can't we just take the complement, 1 minus the probability of rolling a 7 with 2 dice, and that would equal to 1 minus 1/6, and that in turn would be, beautiful, 5 out of 6. Okay, we're going to do this last part, E, after we do our table. All right, so here we go. Remember all of the different sums that we got. This time we're not going to repeat them. So basically, with 2 dice, the smallest value is 2. You can do a 3, a 4. You can roll a 5, a 6, a 7, an 8, a 9, a 10, an 11, or a 12. Cool so far? So, what's the probability of rolling a 2? That's getting snake eyes, right? 2 ones. And there is only one way to roll a 2. Does that make sense? So this is our only 2 right here. This is the only 2 in our sample space. Good so far? So there is a 1 in 36 chance in rolling a 2. All right? Okay, so what about the next one? Probability of rolling a 3? Well, if you look here, there's 2 ways in which we can roll a 3. And so this one would be 2 out of 36. I'm not going to simplify these fractions so that it'll be easy to verify that our model sums to 1. Okay, we already found the probability of rolling a 4 in part A. And remember, that was 3 out of 36. What about the probability of rolling a 5? Good. That's over here. And that's 4 ways out of 36. And then the probability of rolling a 6. Let's see what we get. We've got, that was 5 out of 36. And then 7s we already found, remember, and that was 6 out of 36. And let's look at 8s. We can get 8s 5 ways. Nines we can get, running out of colors here, we can get 9s in 4 ways. Tens are, let's see, I don't think I used this one yet. We can get a 10 in 3 ways. And we can get an 11 2 ways out of 36, and there's only one way to get a 12. In 36. So if you add up all the numerators here, what's going to happen is we will have what? 1, 3, 6, 10, 15, 21, 26, 30, 33, 35, and 36. So we get 36 out of 36, which fortunately equals 1. Let's check out how we could make a probability histogram. So with a probability histogram, what we're going to do is it's going to actually look a little bit like a bar chart, but the context of, our conversation here will let us know that it is a probability histogram, okay? So with a probability histogram, it's going to be useful to get the percentages. So I went ahead and I got all of these percentages for us. Okay, so now we've got our setup to make our probability histogram, and our highest percentage is 16.67%. We are going to put down each of the possible rolls that we can have. So I'm going to just do kind of a little tick mark. Remember, there were, we could roll 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 11 different rolls that we could do. So let me try to space these things. There was, a 2.78% chance for a 2. So 2.78 will be about here. I'm going to go ahead and finish these off. If you want to fast forward the movie, you can, or try doing it yourself and then fast forward and see how you did. And I'll see you in a minute. Okay, so Next up, let's figure out, expected value and all that good stuff. I've taken the liberty of doing this table, and this is very similar to something else that we did. What else did we do that looked like this? Mean from a frequency table. So this time we actually have our x value, and so instead of multiplying it by our frequency, we're really kind of multiplying it by our relative frequency. So here, x times p of x is kind of similar to relative frequency, isn't it? Times x. And what did we do? If you do all of that, what happens is you get a mean roll of 7.2. So the expected value, or I guess we could think of it as the expected sum, is actually the sum of all of our x's, right? So this 1/18 is a result of my 2 times my probability of rolling a 2 equals 1/18, okay? And so when you sum all these up, you get the expected value sum of rolling 2 fair 6-sided dice is 7.2. So why do you think in craps a 7 is bad when you've got, a bunch of chips on the table? Well, because that's the most likely roll over time, right? If you roll 2 dice a bunch of times and you record the roll, the sum of the roll, and you'll find out and get the average of all those sums, you'll find out it's going to be about 7.2. So here's our theoretical expected value or mean. But I bet if you did an experiment with 2 dice and rolled them, say, 100 times and recorded the sum of the 2 dice each time, and then added them all up, divided by 100, you'd get about 7.2. Isn't that groovy? Okay, so now the spread. How do we figure out the spread? So the spread this is all theoretical, right? So that's why it's in terms of mu and sigma squared. So I showed you this way here just because it's easier on a table to do. I think it makes more sense to do this way because then you can actually see you're subtracting the x value, right, from the mean roll, okay, and you're squaring it, so you're figuring out how far each individual roll is from the mean, and then you're multiplying it by its associated probability, and then you add them all up. So what will happen is this is right here. This is the setup for finding sigma squared, and when you add everything up, this is equal to sigma squared, and that's probably approximation, sigma squared. So if I want to find sigma, what would I do? I would just square root that. So if we do that, it's going to be 2.544, but usually you just go 1 digit past what your x is. So again, sigma, a better answer for sigma squared would be approximately 6.5, and that gives us sigma approximately 2.5. Cool? All right, so now let's look at binomial probability distributions. These are kind of a simplified deal. You either have a success or you have a failure. Density function has a finite number of trials with two possible outcomes, often referred to as success or failure. And the probability of success in independent trials remains the same. So they're independent trials. So that's a little redundant to say that because that independent, remember, you had to have the same probability of success to be independent. Now, when thinking of the independent trials, X represents the number of successes out of the independent trials. I guess we could say capital N here. All right, so let's suppose, unfortunately true, that Shannon's oven is not working properly, and the probability of not burning a batch of cookies is 0.52 each time she attempts to bake a tray of cookies. What is the probability that Shannon does not burn exactly 2 batches of cookies in 3 attempts? All right. So, however we want to say this, you can either define what a success means, or, I don't know, you could either burn or you don't burn, right? So the success in this case would be not burning. So we could say let S denote the event of not burning a batch of cookies. And of course, the, F, of course, would represent the event of burning a batch of cookies. All right, so what's going to happen here? These are independent trials. Okay, we're going to assume independent trials. And what we're going to do is check out what happens, what could possibly happen in 3 attempts. If we listed out our sample, or possible samples, I mean, you could have success, 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 failure, success, failure, success. See what I'm doing here? And you could have failure, success, success. So I've listed all the ways you can have 3 good trays of cookies and 2 good trays of cookies, right? All right, and let's list the number of ways we could have 1 or 0 successes. So that's 0 successes. And then these are the number of ways we could have 1 successful batch. Cool, cool. So those are all the possibilities that could happen. So now let's find the associated probabilities. The probability of all of them being successful is going to be 0.52 times 0.52 times 0.52, or isn't that the same as 0.52 cubed? Good. 14.06%. And then let's check out this next one. This would be approximately good. 0.52 times 0.52 times, what's the other one? Probability of a failure is going to have to be equal to 1 minus the probability of a success, right? Which would be 1 minus 0.52, which is 0.48. So we'd have this situation here. And why don't you try to figure out the rest of them? And then check yourself and see if you're right. Okay, so this went a little bit above and beyond our purpose. But what we are looking at here, we want to know the following situations. Do you remember? We wanted to know that she does not burn exactly 2 batches of cookies, right? So success is not burning, and exactly 2 batches means exactly 2 batches would mean we'd have 1 failure and 2 successes. So these are the situations where we have 1 failure and 2 successes. And remember, the general addition rule tells us that if you have independent events, you just sum the probabilities because there's no intersections. So so the probability of burning only 1 batch is equivalent is approximately 35.94%, and I just added up those 3 blue ones. Cool? Alrighty then. So in statistics ease, the binomial probability formula is probability of x is n factorial over quantity n minus x factorial times x factorial times the probability p of a success raised to the x times the probability of a failure, which is q, raised to the n minus x, where x is equal to 0, 1, 2, all the way down to n, meaning the number of successes for x. All right? So You can also write this as P of x is equal to n choose x, that's this part of it right here, times p to the x times q to the n minus x. And this is a selection on your calculator, which you can find under math, okay? All right, so notation for the binomial distribution is the mean, or the expected value, is mu equals n times p. N is the sample size, p is the probability of a success, and q is the probability of failure. So sigma squared is our variance, and that's just equal to n times p times q, which makes sigma equal to, very good, the square root of n times p times q. So suppose we've got that 22% of Skittles candies are yellow. A sample of 500 Skittles is randomly selected. Find the mean and standard deviation for the numbers of yellow Skittles in such groups of 500. So let's figure out what we've got. What is our n? Beautiful. N is 500, right? There's 500 Skittles selected. The probability of success is what? Good. 22%. And what does that equal to? Good. 0.22, which makes Q, the probability of not picking a yellow Skittle, is going to be 1 minus P, which is 1 minus 0.22, which is, good, 0.78. So what is our mean? Mu, our expected number of yellow Skittles, will be n times p, right? Which is going to equal to 500 times 0.22, 110. And so how do we interpret that? We'd expect to see, good, 110 Skittles out of the 500. All right, so the standard deviation is the square root of n times p times q. Well, that's going to be the square root of 500 times 0.22 times 0.78. So sigma is approximately 9.3 Skittles. So you want to make sure and put your units in these things so that I wasn't too strict on it the last test, but it's important that you start putting your units, okay? Now, I just remembered that we forgot about this one, or I forgot about this one. So what's the probability of rolling more than a 7? What does that mean? Good. We want to look at the probability of rolling anything that's in this quadrant here, or not quadrant, but all of these possibilities right here. So that includes the probability of rolling an 8, a 9, a 10, an 11, or a 12. And there's no, you can't roll an 11 and a 12 at the same time. So this is just going to be equal to the probability of rolling an 8 plus the probability of rolling a 9 plus the probability of rolling a 10, etc. Got a couple more. So now if we look at our chart, that's going to be, so the probability of rolling an 8 was 5 out of 36, plus rolling a 9 was 4 out of 36, plus 3 out of 36, plus 2 out of 36, plus 1 out of 36. And so that gives us what? 9, 12, 15 out of 36. Which is equal to, we'll simplify this one, which will give us 5/12. So a little under 50% chance of rolling above a 7. Okay? All right, well, have a wonderful morning, afternoon, or evening.